بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله وبركاته. And I would like to welcome you guys to another video with the instrumentation and process control lab. In this video, inshallah, we will have a look at the second objective that hasn't been discussed quite much during the over the last couple of weeks, which is identifying the possible disturbances that might affect the controlled variable and examining the automatic controller response under normal and abnormal operating conditions. Okay? So yeah, because it's actually a part of the exams that you might be asked a question like what we have here in question 2, which says describe the change in the output signal percentage of the automatic flow controller in case if, and we assume a particular case scenario. So as an example, if one of the valves is originally closed and it was suddenly opened, like the bypass valve. Right? Now, a very simple demonstration here is for the flow rate control system. Now, the flow rate control system is basically a very simple experiment in which we have water circulation. So water actually is stored here in this collecting tank B1, and the centrifugal pump is used to transfer the liquid through the piping system by increasing water pressure. Right? Now the water flows through the automatic control valve V6, as you can see here, which is open and closed by the supplied air that we have from here. Yep. The bypass valve, valve number 5, is normally kept closed, which is this valve right here. And the water continues to flow through the piping system. We have here the magnetic flow meter that measures water flow rate. And as we all know, the measured value is sent to the controller as an electric signal. The controller compares the two values, which is the measured value reported by the sensor with the given set point, and that's actually what we have in here. So this is the process value, this is the value reported by the sensor, and this is the set point that is specified by the operator of the system. Okay? Now we all know that the controller will make a comparison between the measured value and the set point, and based on the error or the difference between the two values, the controller will take the necessary action to maintain zero error, like what we see right now. The error is equal to the process value minus the set point. The action is in the form of sending a signal. This is the signal right here, and it is known as the controller output signal. This signal goes from the controller, as you can see here, to the actuator or the final control element, which is in our experiment the automatic control valve. Okay? Right. Now the case is, guys, as we said before, is that one of the important questions that you might have is that during steady state normal operation, right? Like this one right now, the system is running at steady state, and as you can see, everything is mostly smooth. And suddenly a change happened in the system. Right? This change is actually known as the disturbance, guys. Right? So if we go back again to the objective, right? The second objective of the experiment is identifying the possible disturbances in the system which might affect the control variable. Okay? So any disturbance that might be introduced to the system will cause the process value, which is the value right here, to deviate from the set point. meaning that this value might go above the set point or below the set point. And if this thing happens, the automatic controller will try to take the necessary action by changing the output signal. Okay, so the output signal will basically change, which will change the position of the final control element or the actuator. In this situation, this signal right here, the output signal, will tell the valve to either open more or close, or go to fully open position or fully closed position, based on the error. The error, which is the process value minus the set point that we have in here. Okay? Right. Now, if you have a question like this, where you have a possible scenario, like what will happen if during normal operation, the bypass valve, as an example, was suddenly opened. You can see that the bypass valve is kept closed during normal operation. Okay? The second scenario is that P1 speed has been reduced. Okay? If you have a variable speed pump in the process, sometimes it might happen that due to any reason the speed of the pump might be manipulated. Okay, so one of the scenarios is that pump speed has been reduced. The third scenario is that air supply to the control valve, which is an air to open valve, has failed, guys. Okay, as we said before, this valve is pneumatically operated, opens and closes by means of the compressed air supply that comes from here. So the question tells you that if something went wrong with the compressed air supply system, which is basically a compressor and etc., if that system failed and that failure caused the air supply to the valve to stop, what is going to happen to the process and how the automatic controller will respond to the change in the process. Okay? And the last one is a liquid level, or the liquid level in tank B1, which is a collecting tank, was significantly reduced. Okay? So we are basically talking about a change in water level inside this tank. Okay? Right. So the way to answer this question logically, guys, because it might be a little bit confusing, is to follow the strategy that we have here on the board. Okay? So if there is a change or a disturbance that has been introduced to your system, you would like to know how this disturbance will affect the process value and how the automatic controller will respond to that change. So in order to answer this question correctly, guys, first of all, you need to recognize the change. Okay? So basically, if there is a valve that has been open and it was closed, we need to know where this valve is located on the process. If there is a pump that was running and due to some reasons has stopped, then we need to know where this pump is located on the process. Okay? The second step, guys, is that once we recognize the change and we understand this particular change or disturbance that has been introduced to the system, we would like to determine how this change will affect the process value. Because as we said before, guys, during steady state normal operation, the process value is equal to the set point. And once the change has been introduced to the system, then the process value will deviate from the set point. It will either go above the set point or below the set point. Okay? And that brings me to the third step, which is calculating or determining the resulting change in the error. Okay? Based on how is the process value will deviate from the set point, we will determine what will be the change in the error itself. And the error, as you can see, is equal to the process value minus the set point. So if the process value goes below the set point, this means that we'll have a negative error. If the process value goes above the set point, this means that we will have a positive error. Okay? Once the error has been determined, guys, the fourth step, will be based on the kind of controller action. Okay, for control actions, gentlemen, we have two types of control actions. The first one is called the direct control action, which is not the one implemented for our experiments for the flow rate and level. The second one is the one we have for the flow rate and level control experiment, is the inverse control action. Now in the inverse control action, you will notice that the controller output signal is inversely proportional to the error. What does that mean? It means basically if the error is positive, meaning that the process value is now getting higher than the set point, you will see that the output signal will start to decrease. Okay, you can see that this is what we exactly mean, or this is what exactly meant by the inverse action. If the error becomes positive, meaning that the process value is increasing above the set point, you will notice that the output signal will start to decrease, and vice versa, guys. So if the error becomes negative, meaning that the process value started to drop below the set point, you will notice that the controller output signal starts to increase. If you follow this logic, then it is very likely that you will get the right answer, inshallah. But before that, guys, for steps number 1 and 2, you have to be familiar with the process, and that requires you to read the process description and review the process flow diagram that we have in the training manual, plus the what is shown here on the cabinet. Okay, right. Now let's take one of the scenarios, gentlemen. So we'll take the first scenario and then we will apply the logic that we have here on the board. So for the first scenario, the question says, determine the change in the output signal of the controller if the bypass valve was suddenly opened. Okay, so the system, as you can see right now, is running at steady state. The process value is equal to 5%, and it is matching with the set point, right? And as you can see right now, this is V5, the bypass valve, and it is currently in a fully closed position. So now, once I open this valve, what's going to happen, guys? So we understand the chain, that this is the bypass valve in the flow rate experiment. Once we open it, what's going to happen is that instead of one valve being open or partially open, now you have two valves being opened. Two valves being open means definitely that the flow rate will increase. Okay, now that brings me actually to step number 2, which is how the change affects the process value. So if we open the bypass valve, we will see that the process value starts to increase above the set point. Okay, and from step number 3, we can easily tell that in this scenario the error will be positive, and that's why for the inverse action you will see that the output signal will start to decrease. Okay, because if you open the bypass valve, valve number 5, the flow rate value measured by the sensor will be sent to the controller. The controller will calculate the error, and once it finds that there is a positive error, meaning that the process value is above the set point, it will try to bring the process value back again to the set point by closing the valve, the automatic valve. Remember that the controller is connected to the automatic control valve, so that will, the output signal will decrease, telling the control valve to close in order to bring back the process value to the original set point. So with the help of the trend, we will see, guys, that this is what's gonna happen. If you notice, guys, the red line and the yellow line are equal to each other. Okay, it will be a little bit difficult to see the yellow line because they are both at 5%. But once I make the change, which is basically opening the bypass valve, you will see right away that the process value has started to increase, as you can see right now. Okay, and the output signal will decrease. So if we write -2, okay, just have a look how we have a peak here, how we have a very huge change in the process value. Now what's happening here, guys, is that the controller, once the bypass valve has been opened, it started to calculate the error. The error is equal to the process value minus the set point, and since we have a huge positive error, you can see that the output signal has started to decrease right away, and it is actually right now reading 0%, meaning that the controller has decided to completely close the valve, the automatic control valve. Okay, so yeah, the question is basically about the change in the output signal. Okay, it doesn't really matter if the process value returned back again to the set point or not. I'm asking you only about how the output signal will change. Okay, now what I'm going to do is that I will close the bypass valve again. Let's do it gradually. Okay, so you can see right now, once I close the bypass valve, the process value started to decrease, and then suddenly it went below the set point, actually, if you can see here. And the moment it went like below the set point, you can see that the output signal has started to increase. Okay, all right, gents, so again, with the bypass valve, opening the valve means more flow rate, which means the process value becomes higher than the set point. This means that we have a positive error, and with the inverse action, we will expect with a positive error that the output signal will decrease definitely. Okay, let's have a look at the second scenario, gentlemen, which is basically assuming that P1 speed has been reduced. Okay, all right, so for the change, or for recognizing the change, which is the first step over there, okay, we need to know what's going to happen when P1 speed gets below the normal speed. So it is very simple, actually. Once you reduce pump speed, you will notice that the flow rate will decrease. Okay, because reducing the speed of the impeller will definitely reduce the flow rate through the system. So a reduction in the flow rate means that during steady state operation, we will expect to see the process value going below the set point, like this. Okay, and going below the set point means that we will have a negative error, and for the inverse action, we will see that the output signal will start to increase. Okay, guys, with the negative error, as we said, we will see that the output signal will start to increase. Now we are back again at the process value of 5%, and it is equal to the set point specified in here. So if we played with pump speed, guys, by adjusting this knob right here, you will see that I reduce pump speed. You will see right away that we have a slight drop in the process value. Okay, and let me make a significant reduction, like so, just to make it clear for you. So by reducing pump speed, as I said, the flow rate will decrease, and you can see right now that once we have a negative error, which is the yellow minus the red line, which is the process value minus the set point, the output signal started to increase. Okay, so again guys, reducing pump speed causes the process value to go below the set point, and that creates a negative error, and as a result of that the output signal started to increase, as you can see here. All right, now I will try to bring back pump speed as it was before. So you'll see increasing pump speed actually right now will cause the process value to increase, and that will bring the output signal down. Okay, the higher the speed, the higher the flow rate, so that's why the control valve will get closed slightly. Okay, gents, so I will try to make sure that the discharge pressure was actually 2 bars at the beginning of this experiment. Okay, and let's give it a few seconds for the system to stabilize, and then we will introduce the third disturbance, which is basically a failure, guys, in the air supply to the control valve. Okay, so the third scenario is that air supply to the control valve, which is an air to open valve, has failed. Now we need to explain a little bit about the air to open valve. Okay, now for the control valves, gentlemen, the control valves are designed to have what is known as the fail-safe position. Okay, which is basically the original position of the valve. Now some of the control valves are originally designed to be in a fully closed position, and the supplied air to the valve will open the valve. Okay, so for an originally closed valve or a failed closed valve, it is also called an air to open, because it is originally closed and you are supplying air to the valve in order to open it. Okay, now this valve right here that we have is a failed closed valve or an air to open valve, meaning that if we cut off air supply to the valve, then the valve will return back to its original position, and it is basically the failed closed, or it goes to fully closed position. All right, so this is, by the way, one of the scenarios that might happen in most of the chemical processes. Okay, because the air supply system is quite huge, guys. So we are talking about compressors and filters and etc. with the piping system, and it is very likely that sometimes the air compressor might fail. Okay, so the change that will happen, guys, in this scenario is that the air supply to the control valve will stop. Okay, and that will result in making the valve or returning the valve back to its original position, which is a fully closed position. Okay, now if the valve goes to a fully closed position, what's going to happen, guys, is that since this valve is closed, the bypass valve, and the automatic control valve is closed as well, the flow rate will stop through the system. There will be zero flow rate, meaning that the process value will decrease. The flow rate will decrease and it will eventually record the zero value. Okay, so it means basically that the process value will go below the set point, and since we have a negative error in this situation, then the controller output signal will start to increase. Okay, now I will have to do this real quick, and don't really have to worry that much about the pump, because the discharge pressure is actually very low. It's not at maximum speed. So what's going to happen here, guys, is that I will close the air supply valve. Okay, and then I will vent the air. Look at the valve right now, it's showing 44%. Now once we vent the air, okay, you can see right now that the valve is returned back to its original position, and that is the fully closed position. So we have zero flow rate right now, as you can see, and if you look at the trend right now, you will see that the process value is actually getting very low. Okay, and the output signal is soaring high. Actually, it's going to the maximum. Okay, so you can see right now that the process value went down very quickly and the output signal is increasing drastically. Okay, so let's try to see what is going on actually. All right, this is for the output signal, and you can see, guys, that the change that has been made in here caused the process value to go to 0. The output signal started to increase and it has reached the saturation value, which is 100%. So what happens here, guys, is that the controller is sending a signal to the control valve, telling it to open. But the problem is that there is no air supply to the control valve. Okay, so once you see that the output signal has increased to the maximum value with no response from the process value, then most likely this is a problem in the air supply to the valve. Okay, now I have to be careful a little bit in this situation, because in order to bring back the process value, you can see it's 100%. I need to put 40%. I have to switch it to the manual mode. Okay, and open the air supply valve again. And I'll close the vent of the regulator. And you can see right now, guys, that once the problem has been fixed, the process value is showing now 4%. I am in the manual mode. I'm running the system manually. So I will bring it back again to the automatic mode. I will just slightly increase the output signal like so. And then once the process value becomes so close to the set point, it is now completely safe to switch to the automatic mode. Okay. Now in this situation, guys, if you notice a huge change or a huge increment in the output signal with no response from the process value, then it is most likely that we have a failure in the air supply to the control valve, and that's why the bypass valve is installed here. Okay, so the field operator needs to head immediately to the field and open the bypass valve, and along with that he needs to communicate with the control room operator to adjust the position of the manual valve, because this one is open manually, in a way that the process value is equal to the set point. Now let's have a look at the third scenario, which is the liquid level in, or the fourth one, which is that the liquid level in tank B1 was significantly reduced. Okay, I kind of apologize, but it seems a little bit difficult to drain some of the liquid from here, but I will try to explain what's going to happen, guys. So for the change in liquid level in this tank, guys, will affect the suction pressure of the pump. Okay, there is a direct relationship between liquid level inside the tank and the suction pressure of the pump. So if some of the liquid from this tank has been drained, the water level inside the tank will drop, and that will result in a drop of the suction pressure of the pump. And we all know that a drop in the suction pressure means that the discharge pressure will drop as well. Okay, so if the discharge pressure drops, then we expect the flow rate to become less in this situation. Okay, and if that happens, guys, you will see that the process value will drop below the set point, and if it drops below the set point like here, you will see, guys, that this is a negative error, and as a result of that we will notice a slight increment in the controller outputs. Okay, so again, I apologize because it is a little bit difficult. I have to stop recording right now in order to drain some of the water from this tank, but this is what is going to happen. If we drain some of the liquid from the tank, the suction pressure will be reduced, and as a result of that, and because the pump is running at a fixed speed, the discharge pressure will drop as well, and that will cause the flow rate to decrease in my system. And because of the drop in the process value or the flow rate, you will see that the output signal will start to increase, or in other words, the controller will tell the valve to open more in this situation. Okay guys, so that was it for the flow rate control. Now I will try to manually, guys, change the experimental setup. So we have the level control experiment. Now I will have to manually, I have to switch now to the manual mode, okay, and I will manually reduce pump speed, okay. I will close the control valve because in the level control experiment, liquid level control experiment, we will use the variable speed pump as an actuator. In the flow rate experiment, the actuator was the control valve and the pump was running at a fixed speed. Okay, so a couple of changes that can be made in here. So I'll close this valve as well, and I will open this valve. You can see right now that water starts to flow into the tank, and yeah, most likely I'll keep the outlet valve at this position. So with this experimental setup right now, with the level control, the objective of the experiment is to control liquid level inside this tank B2 at different set points by manipulating water inlet flow rate to the tank using the variable speed pump as an actuator. So for now, let's just imagine, gentlemen, that there is no automatic control valve, because with the variable speed pump you don't need an automatic control valve. Okay, so the level, as we all know, guys, in this kind of tanks, which is a fixed roof open to the atmospheric tanks, the level is affected by the inlet flow rate, okay, and the outlet flow rate, how much is flowing into the tank and how much is flowing out of the tank. For steady state constant level, the system has to make sure, or the control system has to make sure, that the flow into the tank is equal to the flow out of the tank. Now we have the level sensor that measures the level inside the tank, and the measured value will be transmitted to the controller as an electric signal. The controller will compare the two values, and based on the difference between the two values, it will decide what action needs to be taken. Let me just change now from here the control variable, which is the level, and the actuator in this experiment is the variable speed pump, as you can see right now. Okay, so once the controller compares the measured value with the set point, based on the error, the controller will send the signal to the final control element, or the actuator, which is in this case the variable speed pump. So pump speed in this situation will be changed either by increasing it or decreasing it based on the given level in this experiment. Okay, let me do a couple of things before I switch to the automatic mode. So for the liquid level controller, we have to determine the PID settings, which is basically 0.59, 0.58, and 0.0015. Okay. Okay, Jess. So the first set point that we have is, as an example, 10%. Okay, and we need to control the process remotely, so this is the actuator, and we'll select control. So as you can see right now, pump speed is actually very high. I forgot to change it. Okay, let's go back again to 5%. It takes a while to start up the system. Okay, and by the way, we have to make sure before we make any change, guys, that the values here are correct. As you can see here, I didn't change the output signal. It was 44 for the flow rate experiment. So that tells me, guys, that the actuator characteristics is very important in order to understand how the system will respond to that change. The output signal that goes to the controller is kind of different from the one that goes to the variable speed pump. Okay. So let's give it a few seconds, and once we get very close to 10%, then we can safely switch to the automatic mode. All right, and after that, inshallah, we will try to see what kind of disturbances we might have in this experiment. Okay, so if we go now, if we switch to the automatic mode right now, so I'm kind of close to the set point, right? So let's give it a few seconds, and then inshallah we will see how the system will respond to some of the disturbances in this experiment. Okay guys, so let's have a look at the process trend. Okay, that was for the manual control. And the spike right here is when I made a mistake. Okay, I didn't change the output signal. It was for the flow rate control, and you can see that the process value went up so quickly. The level went up so high in just a few seconds, and that's why I had to manually reduce the output signal from like 44%, I guess, to 5%. So the level started to go down. Now let me just prepare everything for you here. Okay. Alright. That's 3, that's 2. Okay. Okay, yes. Now let's try to, instead of the 10% set point, because the output signal is so low, I will try to change the set point to 20%, so we can have a better understanding of the changes in the output signal at a higher set point. So as you can see right now, guys, a change in the set point is an example of a change in the process. Okay, so for the changes in the process, it could be a change in the set point or a disturbance that has been introduced to the process. And so as you can see right now, once I change the set point to 20%, the automatic controller started to calculate the error, which is the current measured value with the set point. It is a negative error. So you can see for the inverse action, with the negative error, you will see that the output signal will start to increase. Okay guys, so as you can see right now, the process value is at 20%, almost matching with the set point, and the output signal from the controller is at 7%, right? So let's have a look at some of the questions in the liquid level control experiment. So the question says here, describe the change in the output signal of the automatic level controller if, as an example, V14 has been completely opened. So the first thing that we need to know is recognizing the change, which is basically trying to locate V14. This is V14, guys, and it's basically the outlet flow valve. Okay, as you can see right now, this valve is partially open. So the question says, what will be the change in the output signal if we suddenly open the valve fully? Okay, now once we open this valve in a fully position, what happens is that the inlet flow rate becomes less than the outlet flow rate. Okay, and as a result of that, we will notice that the level will start to drop below the set point, which is 20%. You can see right now, guys, that the process value or the measured value is matching with the set points. You can see the yellow and the red lines. Okay, now once I open valve number 14 fully, what we are going to see is that the level will drop, because as we said, the more you open this valve, the more flow out of the tank, and that brings the liquid level below the set point. So a lower level means that we have a negative error in this situation, and with the negative error for the inverse action, we will see that the controller output signal, which is the green one, will start to increase. Okay, let's do it. So everything is at steady state right now, and I suddenly decided to open the valve. You see that the level dropped a little bit, and you can see it through the trend. You see that the process value started to go below the set point. Now we have a negative error, and as a result of that, the output signal started to increase. So it's basically because there is a drop in the level, the controller is telling the pump to increase its speed. Okay, pump speed is now increasing, as you can see, right? And the system is taking some time right now to bring the process value back again to the original set point, right? So you can see right now that a level is gradually increasing. Okay, it's now 15%. It's now 16%. It's getting closer to 16, I guess. Yeah. Okay, so if we give it a few seconds, you will notice that eventually the process value will go back again to the original set point. Now let's try to bring this valve back again to the original position. So closing this valve means that the inlet flow rate is now higher than the set point. Okay, you can see right now, once I close the outlet valve back again, the process value went above the set point. This is now a positive error, and as a result of that, the output signal started to decrease. Okay, so the system will take some time trying to bring back the process value to the original set point. Okay, and as a matter of fact, we have to be careful here, guys, because when we have a huge positive error in this situation, okay, what's going to happen is that the output signal, as we have seen, will decrease drastically. So once we have a drop in the output signal, the pump speed will decrease, and that causes the discharge pressure to become very low. Okay, now the dangerous thing about this situation here, guys, is that in this situation, if the discharge pressure at the pump became less than the pressure here, okay, let me try to show you through the process flow diagram. If the discharge pressure here at the pump became less than the pressure here, okay, we know that there is water inside the tank, and that will create some static pressure. Okay, so if the pressure here became larger than here, then we will have a reversed flow, and that is a serious issue when it comes to pump operation. Unfortunately, the training equipment has not been equipped with a check valve or one-way valve. Okay, and that's why we have to be very careful during the operation of the system, or even if you want to shut it down. The shutdown procedure has to be done properly in a way that the tank must be empty before you decide to reduce pump speed to the minimum value. So again, it is very likely sometimes if you guys work in a chemical process that you will see some design issues, and in this situation usually the procedure is to request a design change, either by the addition of an equipment, addition of an extra pipeline, or changing an existing pipeline as an example, or changing the size of the pump, or etc. Okay. So as you can see right now, after a couple of minutes, the process value returned back again to the original set point, which is 20%. Let's have a look at the second scenario, which is P1 has stopped. Okay. So what's going to happen if the centrifugal pump stops? Basically, guys, the level is affected by the inlet flow rate and the outlet flow rates. And if we stop this pump, there will be no flow into the tank. And as a result of that, the liquid level will drop very quickly, guys. It will actually get empty. Okay, so this means that the process value will drop below the set point. And if that happens, we will see that the output signal will start to increase, just like we have seen before with the failure in the air supply to the control valve. Okay, so I'm going to do this right now. So as you can see, the measured value is 20%. The set point is also 20%. Let's stop the pump. You see that the tank is getting empty right now, and you'll see that the process value is now getting almost 0%, and the output signal started to increase. Look at it right now. It shows 20%, 21, and it is increasing, and it will continue to increase, guys, until it reaches the saturation limit, which is in this case 100%. So the feedback control system actually doesn't know what is the nature of the disturbance that has been introduced to the system. The feedback control system doesn't know what problem has occurred in the system, guys. All what it knows is that I received a measured value from the sensor, and this value will be compared to the set point, and based on the error I will take an action. Right now the controller is telling the pump to increase its speed actually. Okay, but we have, let's say, some failure in the pump due to which the pump has tripped. Okay, now in this situation again, guys, let's go back and remember the last process value before the pump was switched off. So it was somewhere around 7%. We have to switch it to the manual mode and write 7% like so. Okay, and then, because as we have seen, guys, if we switch on the pump while the output signal is very high, we will see a huge increment in liquid level inside the tank. Okay, so we'll switch on the pump back again, and I'm doing this manually, guys. You can see that if we have an emergency in the system, we have to switch to the automatic mode. And from the history of the process or the trend, we will try to see before the problem happened what the output signal was. Okay, so it's basically known that for the last good PV, what is the output signal? As you can see now, the system is returning back again. Okay, so let's give it a few seconds and then try to switch to the automatic mode once the measured value is matching with the set point. Okay, so now it's increasing, so I will switch back again to the automatic mode. Okay. So now the automatic controller is now calculating the error, and based on that, as you can see, since we have a positive error, you'll see that the output signal will slightly decrease. Okay. The change here depends on actually two factors, gentlemen, which is the magnitude of the error Okay, if it is a huge error, then you will see a huge change in the output signal, and how the automatic controller is being programmed, or the proportional integral derivative controller tuning. Okay. So for the three figures in here, guys, the controller tuning, what is called the controller tuning, is actually the scope of the chemical engineers. So from the bachelor degree and above, they are responsible of studying the nature of the system, the characteristics of the system, and based on the components and the nature of the process, they will determine from the PID settings how the controller should respond to a change in the disturbance. Okay, so let's give it a few seconds and then have a look at the third scenario, which is not to be covered actually. It says that if the control valve in this experiment has been opened, I'm not going to do that actually, but or you know what, let me do it. Okay, so let's say that the control valve here has been suddenly opened, right? So the supply pressure to the control valve is, as you can see right now, the control valve is fully closed. Okay, but let's say that someone during the experiment accidentally, instead of increasing pump speed, decided to open the automatic valve. In this situation, guys, we all know what's going to happen. Now you have two valves open. That causes the flow into the tank to increase, meaning that the level will go above the set point, and as a result of that, we will see that the output signal will start to decrease. Okay, so you can see that valve position right now is almost 0%. I'm going to open it just a little bit like this. Okay, you can see it's now open, 53%. Okay, and it could be due to the fact that pump speed is very low actually. Okay, it is difficult to measure this change because currently, guys, pump speed is very low, but you can see this. You can have a look at this, guys. You'll see that there is a slight increment in the process value and a very slight drop in the output signal. Okay, but if the pump was running at a higher speed, then we will see a significant change in the position or in the output signal that goes to the pump. Okay, so the flow rate right now is like 911 at a fully open control valve. Let's see what's going to happen when we close the control valve. Okay, so yeah, there is almost no change in the flow rates. So it was almost around 900 something. But again, as I said, guys, if the pump was running at a much higher speed and the control valve was suddenly opened, now we will have two valves being opened. That means more flow into the tank, and you'll see that the output signal will start to decrease. Okay, gents, so the last question is about V11 has been opened. Okay, let's try to have a look at valve 11. So this is the process, the beginning of the process. Water flows through the bypass valve and then through V7 and then V9, V10. This is a safety valve, pressure safety valve. Now this is V11, guys. Okay, water is supposed to flow through the piping system through V12 into the tank or tank V2, while V11 is closed. Okay, now as you can see right now, V11 is in a fully closed position. And yeah, speaking of how to tell if the valve is fully open or fully closed, guys, it's very simple. Just look at the handle and try to see what angle the handle makes with the pipeline. Okay, if it makes a 90-degree angle like this, okay, then this means that the valve is closed. If it is parallel with the pipeline like so, okay, like B12, and this means that the valve is open. So the question says, guys, that during normal operation, what's going to happen if V11 is opened? Okay, if we open this valve, then you will see, guys, that some of the water will start flowing back again to the tank. That causes the inlet flow rate to the tank B2 to drop. And as a result of that, we will see the level going below the set point. Okay, and again, that will generate a negative error, and as a result of that, we will see that the output signal will start to increase. Let me show you again, guys. If we open this valve, water will start to flow back again to B1 instead of flowing to B2. Okay, so there will be a significant reduction in the inlet flow rate to B2. Okay, let's do it right now. So I just opened V11. You can look at the level. Okay, it's now going below the set point, and you can see it right here. So the process value is now going below the set point. That makes a negative error, and for the inverse action, you will see that the output signal will start to increase. So what's happening right now, guys, is that with the increment in the output signal, the controller is telling the pump to increase its speed. Okay, let's have a look at the flow rate. You can read it's now 1,900 and increasing. Okay, now it's reaching 2,000 liters. Okay, and we'll continue to do that until the process value is brought back again to the original set point. Okay, now in this situation, as you can see, guys, the output signal, the previous output signal in the steady state operation is very low compared to the output signal right now. Okay, the output signal is increasing. Okay, in this situation, it is highly recommended that in order to bring back the system to the normal situation or the previous situation, to switch back to the manual mode and then try to have a look at the output signal. It is almost 6%. It was 39. Let's go to 33. Okay, let's go to then 25. Let's go then to 17. Let's then go to 12. I'm doing this gradually. And then let's go back again to 7%. Okay. And we close the valve, V11. So you can see right now that the flow rate is actually going to B2. Okay. And that's why you'll see that the level will start to increase. And I'm doing this manually, so let's hold on and wait for the process value to become very close to the set point, and then we can switch to the automatic mode. Okay. The process trend actually is a very powerful tool. It doesn't show you actually the history of a process. It would rather tell you if there is a problem or unusual behavior in your process, guys. Okay, so as an example, you work in a process like this process, guys. Okay, you have a tank and you are used to notice that at, let's say, 40% level, the output signal is 10%. Okay, you have been working for so long, and every time you notice that at 40% process value, the output signal is 10%. But after a couple of months, you notice that at the same process value, 40%, the output is not 10, it's now very close to 20. Okay, that will tell you right away that there is something wrong with the process. Okay, and I'm going to show you one of the biggest problems and one of the most difficult problems to be detected in the chemical processes, guys, which is basically the fact that some of the pressure safety valves, this is the pressure safety valve we have in here, might get stuck open. Now we all know that the pressure safety valve is used to prevent overpressure in the system. Okay, so every equipment you have in the system is designed to operate under a nominal operating pressure or a normal operating pressure. If the pressure reaches a maximum determined value or a predetermined value, then in order to protect the equipment, the safety or the pressure safety valve is supposed to open, guys. Okay. Now, one of the problems that might happen with the safety valves, guys, is that they open and then they get stuck open. They don't get closed again. Okay. And it is actually very difficult to detect because, as a matter of fact, as you can see in here, there are no instruments upstream or downstream of the safety relief valve. I have no pressure gauges or no flow sensors after the safety relief valves. So if it gets stuck open, guys, you might see that the process value is at the set point, okay? But you will see that the output signal is, the change in the output signal might be somewhat abnormal, okay? So as you can see right now, the process value is 20%, and the output signal is around 4.9%. So what's going to happen in this situation is that in case if this valve V10 is open and gets stuck open, the flow will continue, or the flow will start from V10 and through V10 back again to this collecting tank B1. So that causes the inlet flow rate to tank B2 to drop, and as a result of that, you will see that the output signal will start to increase. Okay, so let me show you. I will try to simulate this scenario. It is actually, yeah, it's a little bit difficult, but if you have a look at process value right now, okay, you can see I just opened the safety relief valve, guys, okay? So you see that there is a drop in the process value right now, okay? And the system is taking the necessary action to bring back the process value to the previous point, which is 20%. And eventually it will do that, guys. But what you are going to notice is that now we have a new output signal that is higher than the previous one. So as I said, one of the drawbacks of the feedback control loop is that the feedback control system does not recognize the disturbance or the problem that might be introduced to the process. Okay. So as you can see right now, the system is taking the necessary action to bring back the process value to 20%. And eventually it will reach 20% and it will stay there. But what you are going to see, guys, is that the output signal is now higher, meaning that the pump is running at a much higher speed, and this is kind of an issue when it comes to energy consumption. Okay, now at the same process value, you are consuming much higher energy to keep the process running at the desired value. So I'm gonna close the safety valve. Okay. So I just closed the valve. That's why the process value is now increasing. Okay. So the best way to know, guys, whether the safety relief valve or the pressure safety valve is stuck open is by reviewing the process trend. Okay. You can see right now the system is, or the process value is almost 20% at a higher output signal. Okay. So yeah, it's actually very difficult problem to be detected, but that is actually one of the ways to tell whether you have a problem in the process, which is most likely a stuck open safety relief valve. Thank you very much, guys, and I really hope that you learned a lot from this video, and inshallah I will keep posting other videos for the remaining experiments, inshallah, this semester. Thank you, guys.